Welcome. Today, we're diving into the qualifications of clean rooms with a special focus on differential pressure. I'm Dr. S.K. Singh, and together we'll explore why maintaining the right pressure differences is crucial for keeping these environments contaminant-free and functioning at their best. Let's get started. Let's start by understanding what differential pressure really means. It's simply the difference in pressure between two cleanroom spaces next to each other. The main goal here is to control airflow, making sure it moves in the right direction to stop contamination from spreading. Air naturally flows from higher pressure to lower pressure, and from cleaner areas to less clean ones. This keeps things sterile, protects products and people, and supports the cleanroom's classification. Sometimes we use positive pressure to guard sterile products, or negative pressure to contain hazards. Let's look at an example that shows why controlling airflow matters. Our goal is simple. Air should always flow from cleaner areas to less clean ones, and crucially, away from critical processing zones. This helps reduce contamination risks, keeps the environment tightly controlled, and supports meeting regulatory standards. To do this, we maintain a pressure cascade, a series of pressure differences between rooms. For instance, Grade B rooms sit at plus 45 pascals, Grade C at plus 30, and so on, ensuring air moves in the right direction. Let's talk about the two main types of pressure systems in controlled environments. First, positive pressure rooms. These are designed to keep contaminants out. You'll find them in places like sterile manufacturing, aseptic filling, and biotech operations. The goal here is to push clean air in and stop anything unwanted from coming in. On the flip side, negative pressure rooms work the opposite way. They're used where hazardous materials are handled, like potent compounds or cytotoxic manufacturing. These rooms keep dangerous contaminants from escaping. Typically, the pressure difference between areas is around 10 to 15 pascals to maintain this control. When it comes to regulatory expectations, there are some key requirements that almost everyone agrees on. First, maintaining a minimum pressure difference, usually between 10 to 15 pascals, between rooms is essential. This helps keep contaminants out of critical areas. Continuous monitoring is a must, especially in those sensitive zones, along with alarms that alert us if something goes off track. And of course, everything has to be documented thoroughly, with qualification records ready for review. These standards come from a range of global guidelines, all focused on keeping environments safe and controlled. Let's talk about what affects differential pressure in controlled environments. First, HVAC airflow balance is key. Supply air needs to be higher than return or exhaust air in positive pressure rooms. Then, frequent door openings can throw off pressure stability. Leakage paths, like gaps around doors or ceiling penetrations, also cause issues. Dirty filters add resistance, changing pressure too. Temperature shifts affect air density, which changes pressure relationships. And finally, human movement. People moving around can disrupt airflow patterns more than you might expect. Let's talk about differential pressure measurement and the tools we use. Common devices include the Magnehelic gauge, digital manometers, and differential pressure transmitters. These often connect to a building management system, or BMS, for centralized control. We measure pressure in units like pascals, millimeters of water column, or inches of water gauge. For reference, 1 millimeter of water column is about 9.81 pascals. Monitoring can be done manually, but more often it's continuous and electronic, with trends tracked through the BMS. Let's walk through an example of calculating differential pressure in a positive pressure room. We start with the given data. Supply airflow is 2,500 cubic meters per hour. Return airflow is 2,200, and there's a room leakage factor of 250. The key step is finding the excess air, which is simply supply minus return. That gives us 300 cubic meters per hour. This positive excess airflow means the room can maintain a positive pressure, keeping the pressure cascade stable. The engineering principle here is clear. Higher supply airflow creates that positive pressurization we need. Let's look at how we calculate differential pressure between two areas. It's simply the higher pressure minus the lower pressure. In this example, That's 35 minus 20, giving us 15 pascals. This difference meets the minimum good manufacturing practice, or GMP, requirement. It means the pressure cascade is properly maintained, keeping contamination risks low. Typically, GMP calls for a pressure difference of at least 10 to 15 pascals between adjacent zones. Here, grade B is at 35, grade C at 20, a solid example of compliance. Let's walk through the differential pressure qualification life cycle. It starts with design qualification, where we review the HVAC pressure cascade, assess risks, and study room classifications. Next comes installation qualification, verifying gauges, calibrations, and alarm systems are all set up correctly. Then, operational qualification puts the system to the test, measuring pressure, challenging alarms, and checking door recovery. Finally, performance qualification monitors the system in real conditions, analyzing trends and confirming long-term stability. Each phase builds on the last to ensure reliable, safe operation. Now, let's walk through the differential pressure qualification procedure. First, we stabilize the HVAC system, making sure conditions are steady. Then, we measure the pressure between rooms to check the balance. Next, we verify the pressure cascade, confirming airflow moves the right way. After that, we challenge the system by opening doors, watching how it recovers. Finally, we compare all results against set limits, ensuring everything meets the acceptance criteria for safety and performance. When things go off track, corrective actions help us get back on course. We focus on key steps like air balancing, replacing HEPA filters, recalibrating sensors, sealing leaks, and maintaining HVAC systems. Each action targets specific issues, like low pressure caused by HVAC imbalance or sensor drift from calibration failure. These problems can lead to contamination risks or inaccurate readings. Understanding common deviations and their causes lets us troubleshoot effectively and keep the environment stable and safe. Let's talk about alarm conditions and why continuous monitoring is critical. We're dealing with low and high pressure alarms, sensor failures, and the constant need to watch over sensitive areas, like grade A and B sterile zones, high-risk operations, and containment facilities. The systems we rely on include building management systems, SCADA, and environmental monitoring systems. By analyzing trends, we catch early signs of HVAC wear, filter clogging, and airflow issues, all crucial for timely maintenance and keeping environments safe. Let's look at a case study from a sterile manufacturing area. The team noticed repeated low differential pressure alarms between grade B and grade C zones. Investigations showed the pressure difference was just 5 pascals, far below the target. They found a heavily loaded HEPA filter and a malfunctioning return damper. The root cause was insufficient supply airflow, which threw off the pressure balance. After replacing the filter, repairing the damper, and performing air balancing, the pressure difference was restored to 16 pascals. The pressure cascade stabilized, and the area was successfully requalified. Differential pressure is the unseen force that keeps cleanrooms safe and contamination at bay. It controls airflow direction, prevents unwanted particles, and helps ensure sterility, all crucial for meeting strict regulations. To qualify these systems effectively, we need well-designed HVAC setups, precise monitoring, regular calibration, and ongoing maintenance. Together, these elements create a reliable environment that meets global standards and protects product quality. Thanks for joining me today. If you want to explore this further or have any questions, please don't hesitate to reach out. I appreciate your time and attention, and I look forward to continuing the conversation. Thank you.